Okay, good morning. Let's get started. Today we will discuss about cyclic schedulers. We had looked at clock driven scheduling, the basic table driven scheduling we had seen, but today we will see that table driven scheduling has actually some difficulties. We mentioned that last time. Does anybody remember what is the difficulty of a table driven scheduler?
More space.
No, okay, you mean the length of the table.
Then timers have to be.
Okay, that is not really a big constraint.
New task is arriving. It is difficult to schedule that earlier.
Okay, but that is of all clock driven schedulers. The clock driven schedulers are all static. So, new tasks very difficult to handle, that is true, but we are looking at another clock driven scheduler today, the cyclic scheduler. But the table driven scheduler, what were the difficulties other than this? Yeah, see, one is that setting timers. Each time a task completes, you will have to set a timer, right. So, let us see how this can be eliminated by cyclic schedulers, which are very popular for this reason. Table driven schedulers are rarely used, but cyclic schedulers used extensively. So, let us look at this today. So, let us just recapture what we have been discussing last class. We said that, see, there are large number of schedulers that have been in use for real time systems, and these are basically clock driven and event driven. These can be classified into clock driven and event driven. The clock driven ones are the ones where the scheduling points are marked by clock interrupts, isn't it? That is what we had said. The event driven ones are those where the scheduler wakes up when certain events occur, and these events are the starting of a task. I mean, a task has arrived or a task has completed, right. But in one sense you can say that, see, the task arrival also might depend on a clock, like periodic tasks. So, that way a clock might be involved, but otherwise these are purely event driven other than the clock events, right, whereas clock driven ones are solely based on clock events. Okay, let us proceed. This we had seen last time, and then we had seen that in a clock driven scheduling we need to store a pre-computed schedule, and then this schedule is repeated forever, and then to use this scheduler the designer has to develop a schedule, right. But what is the period for which he needs to design it? We discussed it last time. Anybody can remember? See, if we have, let us say, n tasks of period P1, P2 to Pn, LCM. So, why LCM? Yeah. So, we are assuming that the tasks start in phase, and for again the similar condition to occur, right, we have to look at a multiple of them, that is the common multiple, and we look at take the lowest common multiple. But what if the tasks do not start in phase? We said that, see, when they start in phase, different tasks are there. Okay, let me just draw. So, different tasks. So, if they are starting in phase from 0, then after LCM P1, P2, P3, they are all again similar condition will occur, and they will again repeat their occurrence here because these are periodic tasks. But what about there is a phase here, each one has a different phase. Phi 1, let us say after phi 1, let us say the task T1 starts and repeats. After phi 2, task T2 starts and repeats, and the task T3 starts after phi 3 and repeats. So, will the result continue to hold, the LCM result?
Yes.
Okay, the answer is yes, and one of your predecessor batches we had given this as a exercise, it's a bonus problem, and some of them had done this actually, they showed it very easily, and the proof that they had given is there in the book that was worked out by them. So, very simple thing, argument was very simple, just have a look. We will not really go into how to prove that, but please look at it, it is very intuitive. They came up with various proofs actually, but the one that was most convincing and the simplest that we have included. So, the schedule needs to be stored for LCM P1, P2, Pn irrespective of whether the tasks start in phase or they are out of phase. We had seen that these are used in low cost applications, and the advantages are that these are very compact. The algorithm is extremely simple, nothing much actually, based on the clock interrupt. Look at the table, select the next task. These are efficient, very little computation needs to be done each time the scheduler runs. But if we have to talk about disadvantage, I think some of you had already mentioned that today, that these are cannot handle tasks that arrive dynamically. And we had seen that the simplest was the table driven scheduler, and as all of you mentioned that see this table driven scheduler has the disadvantage that requires setting a timer large number of times, and if a task runs for only a few milliseconds or microseconds, that is the one actually in a real time environment, tasks do not run for minutes or hours, they run for few milliseconds or at best some few microseconds or milliseconds, and there this setting a timer each time is a significant overhead, prevents their use in some applications. Now, let us look at the cyclic scheduler, which are an improvisation of the basic table driven scheduling, where that shortcoming of setting a timer large number of times, each time a task starts, look up the table, find out when the next one will run, set the timer for that value is not required. So, let us see how that is achieved, and no wonder that these are very popular. If you look at an embedded industry, you will find that large number of their products use these, and here we have a major cycle which repeats, and the schedule is required to be computed for the major cycle, and this schedule is repeated. But a major cycle is divided into minor cycles or frames. We are not saying right now that whether there will be an integral number of minor cycle, whether the minor cycle will squarely divide the major cycle, we are not really mentioned that, we just said that it is divided into some minor cycles, and here the tasks cannot start running at any point in the clock time, whereas in a table driven scheduling the tasks can start any time based on when the timer interrupt comes. But here you see here that the tasks can run only at the start of a frame or a minor cycle. So, the schedule that is computed is repeated perpetually. So, this is the schedule which the designer has statically computed, and see here that the tasks are all starting at the start of a frame, right. These small lines that you are seeing, these are the minor cycles or the frames, and just see here that this task, the green one, is starting at the start of a frame and also nearing ending at the end of a frame. Similar is this one, but look at the yellow one, starting at a start of a frame but ending somewhere in the half of a frame, right. So, it is not necessary that a task has to run for the entire duration, and those time will be idle basically, right. If a task completes early, can't use a full frame, that much time is idle. But we will see that later, I mean when we look into more details of this, we will see that if it completes early, then we can schedule some of the tasks for which static schedule was not developed. For example, some aperiodic tasks etc. can be accommodated here if part of a frame is empty.
Task has to start only at the start of the frame, so it has that part can start.
Okay, that is for the table. The table stores at the start of a frame, we look at a task and start it. But for a aperiodic task, the scheduler, what, as we will see, it will, if we have to accommodate that, if we have to accommodate aperiodic tasks, it will utilize parts of a frame even, and also all those empty unused frames that are there will be used. That is an extension of a cyclic scheduler, you can say. It is not a basic cyclic scheduler where aperiodic and sporadic tasks run.
But these frames are they similar to clock pulses or something like that?
Yeah, similar to clock pulses, but these are not really clock pulses, these are periodic. Maybe 10 clock pulses is equal to one minor cycle. Yeah, yeah. So, one periodic timer is set once. To start here, at time 0, a periodic timer is set, let us say for 15 millisecond, or 15 millisecond is too much, maybe let us say some 50 microseconds or something, depending on the application. And then it keeps on giving these interrupts every 50 microseconds, right. Is that okay?
Yeah, smaller ones are that.
Yeah, smaller ones are the frames which are obtained through interrupts from a periodic timer. So, the major cycle, let us see what is the length we need to store. Let us say we have n tasks constituting the task set, then again we need to store for P1, P2 up to Pn, and as we were discussing, this holds even when the tasks have arbitrary phasings. But the thing is that if the frame, there is not an integral number of frames in a major cycle, that is f does not squarely divide the major cycle, then we will see that this LCM P1, P2, Pn is not enough. We need to store for longer duration. So, maybe I can give you that as an exercise, that what if the frames do not end, I mean they do not integrally divide. So, what will be the length of the schedule that needs to be stored as a bonus problem, right. It is not there in any book or anywhere reported. So, please try out, what if the frame size does not squarely divide the major cycle, what is the duration of the schedule that needs to be stored. As we will see that to reduce the schedule length, we will impose that there is a integral number of frames in a major cycle, and the frames are marked by interrupts from a periodic timer. So, the bonus marks we will just keep on giving as we proceed, the ones that where you have to think and are not really there in the book or any reported result, you won't quickly find through a Google search or something. So, these those who are able to do, please submit it, and we will, as I announced earlier, we will have special marks, right. But it is not mandatory that all have to submit, etc. No, if you are able to think and submit, please submit, but it has to be your original, right. Okay. So, let us proceed. This looks like a schedule. This is a typical schedule where these are the frames F1, F2, F3, etc. and task T2 runs in F1, T3 runs, and it is not necessary that all frames need to be utilized by some tasks. There are usually many frames will be idle, and a task can run in one or more frames, and as we will see in the subsequent discussion today, that the frame size is one of the important parameters that a programmer has to design. And then based on the frame size found, then he will have to set the periodic timer, which will give the determine the frames. Now, the frame size is to satisfy a few constraints. Let us look at the constraints.
Sir, is it necessary that our task should complete within a major cycle?
Okay. So, the question is that whether the task will complete in within one major cycle. So, what about anybody has answer to his question? Let us hear your answer, then I will give my answer.
Yes.
Yes.
Okay. Why is that? So, you are saying that it needs to complete within a
Because the
major.
task may be comprised of some minor frames, and all the minor frames will make one major frame. So, any task has to.
No, you are saying that a task is having runs on multiple frames and
Okay, and so that it has to make within one major frame. So
not really very
the
convincing.
LCM of all the.
Exactly. Yeah, here is the answer. That see, the major frame, sorry, the major cycle is defined as the LCM of the task periods, right? So, anyway, it will be much larger. It is a multiple of that.
So if one is of 2 and the other is of 4, if time period of one T1 is 2 and the time period of T2 is 4 and the LCM is 4,
Yeah.
then the major cycle is 4, but they both are adding to 6.
Yeah, that is okay. I mean, we are not saying that whether they are schedulable or not. We are saying, see, it is possible that we find a set of tasks which are not, they cannot run, they are not schedulable. But what we are saying is that if they run, the period for which the schedule needs to be stored is LCM of their periods.
There is no notion of preemption, etc.
Nothing. It is just a, these are, see, preemption comes when you talk of a event driven one, right. Here we have stored the schedule, but it might so happen that for schedulability, a designer might say that, see, a task T1 runs and as soon as T2 comes, it completes and then again T1 is taken up. So, T1 is broken up into 2 frames, possibly. But notion of a preemption comes in a event driven scheduler, where certain event comes, we just running task is preempted. So, that concept is not here. It is the pre-computed schedule which will be kept on running. Okay, let us proceed. Let us see how a frame size will be determined. What are the constraints on the frame size? One is we have to minimize the context switch. So, to minimize the context switch, we need to make the task run in one frame as far as possible, because if it is scheduled in different frames, then obviously the context switch overhead will come. So, to satisfy this constraint of a minimum context switch, the frame size should be larger than the execution time of a task, isn't it? Because if the frame size is less than execution time of a task, we will have to run it in multiple frames, and this will set a lower bound on the size of the frame. The other constraint is to minimize the table size, and this constraint requires that the frame size should squarely divide the major cycle, and this constraint, the implication is that we can use or try out only a few discrete frame sizes. For example, if we have fixed the major cycle to be, let us say 20, then we can try out 2, 4, 5, 10, etc. So, there has to be a multiple. The other constraint that needs to be satisfied concerns satisfaction of task deadline. When a task arrives, it has certain deadline, and then the task must complete by that deadline, and the constraint is that at least one full frame must exist between the task's arrival and its completion, right, sorry, its deadline. The task's arrival and deadline, there must exist a full frame, because our constraint is that the task has to start exactly at the frame boundary. So, if there is not a full frame, we can't really run that task, isn't it? Okay. So, this will set an upper bound on the frame size. If the frame size is more than something, then this constraint of a full frame to exist between a task arrival and its deadline may not be satisfied. So, let us look at these three constraints that we identified in more detail. The first one we discussed is minimum context switch, where task instance should preferably complete within its assigned frame. Otherwise, we will have unnecessary runtime overhead, which we do not need. So, a task would otherwise, if it does not complete, it might have to restart it at a later frame, and also not only that, the scheduler will get invoked many times. To avoid unnecessary context switches, the frame size should be larger than the execution time of each task, right? And this will also minimize the number of times the scheduler runs, isn't it? If the frame size is too small, let us say one clock cycle is one frame. So, every clock cycle the scheduler comes up and runs. It is not really very practicable situation. So, let us look at the other constraints. So,
size should be larger than execution time of each task.
Yeah, I mean all tasks together, let us say we have E1, E2, E3, or let us say 2, 5 and 10 are the execution time in microseconds, let us say 2, 5 and 10, 3 tasks, and then we can say that the frame size has to be at least 10. If it is less than 10, then see one task will have to be split into 2 frames.
But the previous another constraint means if a new task arrives,
Yes, its deadline. Yes.
So there should be an optimum level of.
Exactly. So that is what is the designer needs to do, find the optimum level. See, we have a lower bound and also have upper bound. We have to find somewhere the correct frame size. We will try out.
Does not mean correct means larger than the execution time of each task.
Yes, it will be larger than execution of time of each task. See, a task, once it arrives, it is taken off for running after some time, isn't it? May not be immediately, and then it has a deadline by which it needs to be finished. We will see the typical periodic tasks that we will see. See, a task T1 may be handling a temperature sensor event. So, the T1 task starts after some page, and after that it arrives, keeps on arriving periodically, and each time it arrives, it is taken up for running after some time, usually we will see, and then it has to complete by a deadline, and the deadline typically is the start of the next task. It may be different, it may be that it has to complete within, let us say 10 millisecond, and the period is let us say 50 millisecond. The task is repeating with 50 millisecond frame, cycle, but the deadline is 10 millisecond from here. It is possible, but typically we will see that all tasks that we normally come across will have the deadline same as the start of the next task. So, this is the deadline we are talking of, this is the execution time, and this is the period P1. Task T1 has period P1, E1 is the execution time and D is the deadline. For example, P1 might be 50, the execution time might be 5, and the deadline is starting from this point is 50. So, D1 equal to P1 is equal to 50 and E1 is equal to 5. Does that appear okay? So, we will consider all tasks like this.
frames in this?
No, this is just this task characteristic. There will be many tasks like this, T1, T2 and so on. Now, our job is to run that using a cyclic scheduler, and the cyclic scheduler will have to design the frame, the major cycle, all those we will have to design, right. Let us, as we proceed, we will see how to design the major cycle and the frames. So, let us continue. So, the first constraint that we are discussing is to set the frame size by considering the minimization of context switch. Yes, please.
So, here we are assuming that to avoid context switches, the frame size should be larger than the execution task time of each task.
Each task, exactly.
So, suppose if the set of tasks that we have, there
Yes.
is it characterized such that most of the tasks are very less time consuming.
Yes.
Only one task is there which takes a lot of time.
Yeah. That's a interesting question. He says that, see, every task runs within, let us say, some 10 millisecond. There is one task which takes, let us say, 100 millisecond. So, do we really design the frame to be 100 millisecond? In that case, no, all other tasks are wasting that much time. There, no, each frame only one task can run, and all of them are taking only 10 or so, 5 or so, and 90 is wasted for every task. Yes, that is a question we will address in the course of our discussion, very important question, and we will see how such cases can be handled. We have one task which takes too much time to run, and then the other task, if we fix according to this rule that the execution time has to be, the frame size has to be at least as big as the largest execution time, then we will end up in lot of wastage of the processor time, and task set may not be schedulable. So, we will handle that, we will discuss about it. Okay, let us proceed. So, the minimization of context switch, we will set a lower bound of the frame size, and if we make the frame size any smaller, then the context switches will increase, and also the scheduler will run many more times, making the execution inefficient. Yes, please.
Sir, does this context switching occur at every frame or at the end of every task?
No, let us listen to the question. You are saying that when does the context switch occur? Say, context switch, as in a basic operating system, will occur. Okay, let me just ask this question, what is a context? Then we will talk about context switching. Can anybody tell what is the context of a task? What do you mean by? Yes, exactly. The registers, the cache, the memory it uses. Okay, memory etc., they are not really context. The context is basically the registers, right. The state of the processor defines the context. So, when a task is running and we need to start a new task, the context of the new task has to be loaded, and if the current task has not completed, its context must be saved, right, when it will be loaded when it is restarted earlier, restarted at a later time. Is that okay?
So, if the frame size is even lesser than the execution time of the smallest task,
Yes.
then it would not cause the context.
No, see, if it continues to run in the adjacent frame, there need not be a context switch. But what if it runs in multiple frames and in between other tasks run, then there will be context switch. Yes, not preemption, other tasks are scheduled to run, say T1 runs, then T2 runs, and T1's context was saved and T2 runs after some time, right, there will be context switch. Is that okay? Okay, let us proceed. So, the second constraint is minimization of table size, and we had said that, see, unless the frame size squarely divides the major cycle, then we cannot really store the schedule for LCM P1, P2, Pn, it will be much larger. just look at this, that see here between the here the frames are squarely dividing, right. The frame has started here, the first frame, and the last frame has ended here. But in case let us say half of the frame is here, right. So, in that case the green one cannot start exactly at this position, right. It will be shifted, and all these will get shifted, and in subsequent major cycle they will keep on shifting until we have lot of free cycles here, right. So, it will not we cannot really repeat the schedule.
Sir,
Yes.
in the previous slide,
Yes.
we have said that each frame should have a size that is a minimum of all task size.
Okay.
So I cannot see any.
Okay. So, the first constraint that we mentioned, that the frame size should be at least as big as the task execution size. Here we have not drawn it like that, excepting I think the red one which is running here. So, this is not a realistic figure, just to explain this concept. Now, let us look at the third constraint, that is satisfaction of task deadline. So, let us say this Ti arrives at this, Ti is let us say a task name, and it arrives at this point. Now, the frame has already started here, the green one is one frame, and the frame has already started, it cannot run here, and if we want to run it here, the task Ti, its deadline cannot be met, right. So, this is the problem we will face if we do not even have a full frame between the tasks starting and tasks and the deadline, right. In this case, it will surely miss its deadline, you can't do nothing about it. So, this will set a upper bound on the frame size. We can't have large frames, right. We have to have frames which are I think this shows that if a frame is size is too large, then we can't really meet the deadline. Let us not spend time on that. Here just look at this diagram. See here that the frame the task arrived at the just after the frame started, and it could not run. Now, we have reduced the frame size, right, and the task arrived just before the frame has started, and see here there is a full frame available, we can run the task here in this. Here there is no frame, I mean this will be the frame which we can run, but by that time the deadline will be over. So, this is the third constraint, that the frame size can have a maximum certain size, and this deadline this constraint cannot be violated. See, the other constraints we are saying minimization etc., those are desirable, right. A minimization of the context switch, the frame size is the integral multiple of the major cycle etc. So, those are not really very if we violate that, I mean still it might run, but this we can't, otherwise the tasks will miss deadline. Now, let us see what is the implication of this. The tasks are periodic, that is what we had said, we are considering only periodic tasks, and their start time keeps on shifting from their successive occurrences from a frame size. Just to take an example, let us say we have a task T1, let us say we have a frame like this marked, these are the frames, now let us say we have a task which arrived here, and in the next cycle let us say it started at this point, right, because see the clock cycles are here, and what we have marked, the larger lines are actually the frames. So, the starting of a frame to the task's arrival will change from each task occurrence. Now, the question is that what is the minimum time, minimum separation between a frame starting and the task's arrival? This keep on changing for every periodic task, this keep on changing, unless the task arrival time is a exact multiple of a frame size, which may not be the case. It is a multiple of clock size, right. The tasks arrive at multiple of clock size, they do not arrive at multiple of frame size, right. So, what is the minimum difference that can be observed for a task from the starting of a frame? So, the result is GCD of the frame and P1, sorry Pi. So, if we are considering Pi as the task and f is the frame size, then the minimum separation that can be observed for this task is GCD f comma Pi. Now, this again was proved by one of your predecessors who did a course earlier. Not one, many of them actually came up, some of them, one person came with a very nice result, which is also there in the book. So, his argument was very simple. Let me just tell the argument that he had. So, it says that, see, let us say we have this repetition of the frames and then the task, and since okay, let us assume that the constant is violated. So, we will prove by negation of assumption, okay, by contradiction we will prove. So, let us the GCD of f comma P1, let us assume that this is not true. Okay. So, GCD f comma Pi is a multiple of both f and Pi. The f, both f and Pi are multiples of the GCD. The GCD is the highest common factor, right. So, this is a factor, the GCD, okay, let me just write G. The G is a factor of both f and Pi. Okay. Now, let us assume that there is a occurrence of the task at which the difference between the start of a frame and the task is less than G, right. So, we will have the situation in that case that let us say let us assume that they exactly coincide, let us say it is 0, right. So, if we have a multiple of f, let us m into f and Pi into let us say n, some m and n, let us say these are multiples where they actually have a 0, they arrive at the same time, right. So, since both of them are divisible by G, so we can say that m and n, this is a integer, right. So, we can show by contradiction that this that can be only 0, right, it cannot be more than G, sorry, less than G. You please look at the proof on the book, okay, it is given very simple argument, or maybe if you are not convinced, I will just get it onto the slide and we will discuss. So, for every task, the minimum duration from the frame to the task's arrival is GCD f comma pi, and therefore, for all Ti we must have 2f minus GCD f comma pi is less than Di satisfied. Why is that? See, look at this, this is 2f, is not it? Now, let us say this is GCD, right, this is G, the one that you see here, the task has arrived here. This is the minimal separation between the task and the frame, and so 2f minus GCD should be less than Di, right. So, we are saying that between this and this Di should be, so Di can be later than this one, but it cannot be less than 2f minus GCD. So, this is a case which cannot be scheduled, right. So, the Di can occur only later. Now, several frames might satisfy the constraint. As we will see, we will take some examples, and those are called as the plausible frames. Those are the frames which we can actually make use of, but as some of you were just mentioning that even if the frames are satisfied, it does not mean that the task set is schedulable, right. You were saying that, see, there are 4 and 2 and the frame size is 5, how will it run, right. So, we have found a plausible frame size does not mean that the task set is schedulable, and to increase the schedulability we need to choose the smallest frame size, and we will see that the chances of successful scheduling can be higher once we choose a smaller frame size. We will take examples and show this. Let us look at one example here. So, let us consider 3 tasks T1, T2, T3, which have execution time of 1, let us say, millisecond or something, and the period is 4 millisecond and the deadline is 4. See, all of them, the period and deadline are the same, these are typical of all real time tasks, and each of them take 1 clock cycle to run. Okay, this takes 1.5 clock cycles to run, and this has repeats after every 4 millisecond, this repeats after 5 milliseconds, and this repeats after 20 millisecond. So, how do we do it? Let me just do it on the paper. So, the first constraint is that the frame size to be chosen must be greater than all execution times, is not it? That is the minimization of context switching. So, we can choose 2 or greater, 2 millisecond or greater can be a frame size. We can't have 1 etc., because some task will not run in 1 frame, is not it? Now, let us look at the second constraint. The second constraint is that the frame size should divide the LCM of the periods, right. Now, what is the LCM of the periods? LCM of 4, 5, 20 is 20, is not it? Now, this allows us to select frame sizes, valid frame sizes are 2, 4, 5, 10, is not it? These are the allowable frame sizes, considering the second constraint that the frame size squarely divides the major cycle. This is the major cycle. Now, let us look at the third constraint, that there must exist one full cycle between the arrival of the task and the deadline, and we have to consider the worst case scenario in the task arrivals. So, that worst case scenario is given by GCD of f comma pi, is not it? Now, let us try 2. See, we should try from the smaller one, because the smallest one is preferable. If 2 works, then we should use that, we need not look for 4, but if 2 does not work, we will have to look for 4. So, let us see GCD of 2 comma the first task runs for 4, right, it repeats after 4. So, the GCD is 2, is not it. So, 2f, the constant is 2f minus GCD is less than equal to di, that was the constant if you remember, is not it. So, 2f will be 2 into 2 minus GCD 2 is less than the deadline is 4, satisfied for the first task, there will exist at least one frame. Now, what about the second task? The second task GCD of 2 comma 5 is equal to 1, right. So, 2 into f minus GCD will be 2 into 2 minus 1 is equal to 3, and 3 is less than 5, right. So, even for the second task 2 is satisfied. Now, what about the third task whose GCD is equal to GCD, this is 2 comma 20, which is equal to 2, right. So, 2 into 2 minus 2 is equal to 2, which is less than equal to 20. So, all the 3 tasks can use 2 as the frame size, and 2 is the smallest, and we can use that. But one point that we need to consider is that with 2 they are all schedulable, they will run, but if we really want to minimize the number of times the scheduler needs to run, we should choose the maximum frame size, is not it. See, with 2 it will run, but if we let us say try out 4 and we find that even for 4 that runs. So, in that case we will minimize the context switches, not context switches, the number of times the tasks the scheduler needs to run, if we choose 4 as the frame size, that is the implication. Is that okay? Okay, fine. So, let us look at another example. So, since you know how to do it, maybe you can also try. So, that we are looking at 3 tasks. The tasks are, the execution time is 1, 4, 1 and the period is 4, deadline is also 4. So, all of them the period and deadline are the same. First task is 1, yes please.
In the previous example, you have said that we need to take 4 as the period, frame size.
4, yes, if we take 4, then the number of times the scheduler runs will be.
Why only 4, why not 5 also? 5 is a big, more than 4. So, even what is the optimal case? How can we choose? Like
No,
only with 4?
No, see you can try 5 also, because 5 is also a factor of 20, but if 5 runs, for 5 also the task can run, then we can choose 5, that will also minimize it, the number of times it runs. So, maybe we can try out what is the maximum frame size for which it needs to it can run, and that will minimize the number of times the scheduler runs.
The maximum most number.
The maximum frame size for which the tasks are schedulable. Is that okay?
So, we need not, there is no unique answer to this also. Which some say 4 and some say 5.
No, if 5 it runs, see we can try 2, we find that it runs. We can similarly try 4, if we try 4, okay, it runs. Now 5 it may not run, then we choose 4, but if 5 runs we can choose 5.
So instead of starting from 2, we can start from 5. If it runs for 5, then we can choose that itself.
Okay, doesn't matter. Yes, possible. Okay, so please try this one.
choosing the smallest will be the best. Anyway,
No,
we are,
no, what we said is for the smallest frame size, the tasks are likely to run because no, there are likely to be one frame size between the deadline and the task's arrival. A larger frame size it may not run, whereas a smaller one it may run. So the chances of
smallest size, are we first checking whether it's schedulable or not?
by taking the smallest one, we are trying to find out whether this frame size the task can run. Yeah, schedulable basically.
actually, we are not preempting a task, and means we are stopping a task and continuing.
No, all those are fine. They are not. Each task is running in one frame size, etc. All are fine. What you are saying is that the number of times the scheduler wakes up and has to look at the schedule is minimized if the frame size is more. Otherwise, it wakes up and every frame size, and then it just doesn't do much, right? Okay. So, please try this one. 3 tasks E1 T1 has execution 1 period 4, task T2 execution 2 period 6, and task 3 execution 3 period 20. So, first tell me that what is the maximum frame size? Sorry, minimum frame size. The first one sets the minimum constant. So, what is the minimum frame size? 3 milliseconds. Okay. 3 milliseconds or higher. It should be greater than equal to 3. That is the first constraint. Now, what about the major cycle for this? Okay, major cycle is 60. M is equal to 60. Now, what are the possible frame sizes? Yes, what are the possible frame sizes for this? Anybody would like to answer this question? Okay. So, 3, 4, 5, 6, 10, 12 and so on. So, there are many frame sizes, 15 etc. Now, let us look at the third constraint. So, let us look at 3 first. So, will it run on 3? Please try out. The first task, what is the GCD of 3, 4? For the first task is GCD 3, 4 is 1. So, 2 into F is 2 into 3 minus 1 is less than equal to 4. It does not satisfy. Now, let us look at the next frame size 4. So, for 4 GCD 4, 4 is 4. Now, 4 into 3 minus 4 is equal to 8. Oh, sorry. Okay, 2 into, I am sorry, 2 into 4 minus 4 is equal to 4 less than equal to 4. Satisfied, is not it? Satisfied for, is that okay? 2 into 4 minus 4 is equal to 4, which is less than equal to 4. Now, for the second task, if you try out, the GCD 4, 6 is 2, is not it? So, 2 into 4 minus 2 is less than equal to 6, is not it? It is equal to 6. So, is less than equal to 6, is satisfied for second task also, all right. What about the third task? The third task GCD 4 comma 20 is equal to 4, right. Now 2 into 4 minus 4 is less than equal to 20, satisfied. So, all the 3 tasks can run on frame size 4, but not on 3. So, it is not really necessary that they will run on the smallest frame size, it is not necessary. So, let us proceed further. Now, as some of you were saying that what if a task takes too much time and some other task takes too little time. So, that can make it unschedulable. So, a task with a large execution time like 20 and others are 2 etc., they can prevent the smaller task from being frame being chosen, and in this case we will have to split the task with a large execution time into 2 or 3 subtasks. For example, 20, 100, 100. So, 20 is the execution time, 100 is the period and 100 is the deadline, can be split into 10, 10, 10 and 10, 2 subtasks we can consider this to be. So, since this hour's time is up, we will just stop here, we will proceed in the next class. Okay, thank you.